Okay, I think most people have answered. Let's see how this stuff works. And to show you, I'm just going to show you the code. So here is the code that I wrote to finish off these neural network things we were starting last time. And I'm using, as an example, our Connect 3 game. So tic-tac-toe or pig-tac-toe. So I have these functions with k and a line that you guys are all familiar with. I'm doing the 4x4 board, and I'm making a neural network that inputs a board and outputs something. And here is my neural network. It has an input of size 3 times n row by n column. So the number of inputs, remember the neural network is sort of this machine that inputs a vector. The starting vector is 3 times the number of rows times the number of columns. Does anyone want to guess why it's 3 times the number of rows times the number of columns? Yeah.
Because there's 3 states for every cell.
That's right. So every cell can be 0, 1, or 2. And the number of cells is the number of rows times number of columns. And so I'm going to do every single sort of input is going to be, is cell 1, is that an X or an O or blank? Is cell 2, is that an X or an O or blank? And altogether, there's going to be 3 times n row times n column. So here is what the input actually looks like when I go down to the neural network. And I call it 1 hot 0, 1 hot 1, and 1 hot 2. So this is the so-called 1 hot encoding, where it's a 1 if the thing is there, and it's a 0 otherwise. So instead of implementing, like I could have taken the board, and the board has values 0, 1, or 2, but the 1 hot board has values that are true and false. So that's called the 1 hot encoding, and that's what I'm doing here. So each of these on their own is shape, number of rows, comma, number of columns. So they're each 4x4 arrays, same shape as the board. And then I stack them together to make a new thing. So here they are stacked together to make something which is stacked on top of each other. And I said there's 4 of them. That's a lie. There's 3 of them. Let me erase. Let me make this a 3, and then I'll erase this little confusing comment. Okay. So I stacked 3 things on top of each other, the 0s, 1s, and 2s, in some weirdo order for no reason. Okay. And then I did this rearrange thing, rearrange, which does what it says in the comment. It flattens the last 3 dimensions into one single vector. So before it was number of rows by number of columns by 3, and then it gets flattened into something which is number of rows times number of columns times 3, which is exactly the input that I had before. So this altogether is condensing it down to 3 times 4 times 4, also known as 36 inputs into my neural network. And then I do the operations that we talked about last time. Here they're called first, hidden, and output. First is a purely linear operation. It takes the X, which is the input, it multiplies it by this weight matrix W1 and adds V1. Hidden takes what was in the first layer, it applies this non-linearity, breaks us out of the linear universe, multiplies by W2, add V2, and then finally we do output, multiply by W3 and add V3. So I'm doing this ReLU twice, and I have one sort of hidden layer in between. And then I return the output. The output, it turns out, has an extra dimension. So if you run it, you'll see that it's not what we want. It's something comma 1. It's a one-dimensional thing. I just want it to be a number, so I rearranged it to get rid of this operation. Some people call this a squeezing operation. We squeeze out that one dimension. So there we go. And here's another confusing comment. Let's erase the confusing comment before people get confused. Okay. Let's call this one squeeze out the one-dimensional vector to get a scalar output. So there we go. That inputs the parameters in the board, and it's going to output a number. And that number is supposed to tell me how good or bad my state is with the value function. So here it is in action. I make the key. The internet likes to suggest 42 is the key. Params, what were the params? They are all the weights and biases. And I have a function called init params that makes that. Let's go back to that function. So init params, it makes the things that are the right size, so all the operations make sense. So W1 is input size by hidden size. It's like a long rectangular matrix. B1 is just hidden size, so you can add it on, and so on. So all of these are the right size. These have the right sizes so that the operations that I defined already make sense. So in fact, the way I wrote this is I wrote this part first with what operations I want it to do. And based on these matrix multiplications making sense, all of these things have to be the sizes that we're told over here. So for example, that W2 is a hidden size by hidden size. It is a square matrix. Okay. It's a nice idea to scale these so they're not too big. So sometimes you scale them to make sure they're not too big, and that'll make sure the value of most states when we start is close to 0. So here it is. I made 3 random boards. Boards is a random of 0, 1s, and 2s of size and batch by rows by columns. So 3 by 4 by 4, 3 random boards. And it thinks all of the boards are pretty close to 0. That's a good starting spot. If the computer doesn't know anything, it should probably guess something close to 0, not like 7 or something for these things. Okay, so this is a little bit of a recap from last time, but sort of operationally how you define these operations in JAX. And then I'm going to move on to the next line, which is our loss over here, exactly as it was in the mathematize. But questions or comments about that so far? No, okay, let's go on to the loss. So the loss is exactly written as it was in the mathematize. So params, boards, returns. Returns I set to some random value. When you're actually trading, you will run simulations and you will use the returns you see in your games to make the returns. But here I just set them all to 1. I got the boards from before, the 3 random boards. I took the gradient and something went wrong. So when you run it, and what did you guys say? What do you think will go wrong? Here it is. What we think will go wrong is, drum roll, Most people think the thing that is wrong is you forgot to tell JAX.grad which entry is the parameters. So over here, JAX.grad of loss. Loss actually has 3 inputs, parameters, boards, and returns. How is JAX supposed to know that the params is the right one? So the thing that you should do to be extra sure is to write on, let's see if Google knows it off the top of its head. I think you go JAX.grad, argnums equals 0. And if you put argnums equals 0, then it says do the derivative with respect to the 0th entry, which is the params. So argnum equals 0 will cover you and make sure that the computer knows I'm talking about the 0th one. If you wanted to do the derivative with respect to the board, that would be argnum equals 1. So there you go. However, that is not the answer. Does anyone know why that's not the right answer? Yeah.
Grad by default is for the first.
That's right. So if you don't put in anything, then the computer will say they probably meant to do argnums equals 0, and we'll just assume argnums equals 0. So if you just do it like this, as long as you always put parameters as your 0th entry, it's perfectly fine. So that's not the right answer. What is the second most common answer? The second most common answer is because you can't do vector operations on tuples, or because you can't do the gradient of a vector. Those are the 2 second most common things. One of those is right. Let's read the things. This is a good skill. Let's read the error and see what it says. Read the error, read the error. Type error, gradient only defined for scalar output functions. The output had shape 3 comma. So what this is saying is when you try to do a gradient, the thing you're doing the gradient of must be a scalar, must be one single number, and the thing that I saw, the output, was shape 3 comma. This is good to know. What is shape 3 comma? Well, that's the size of the batch. So the batch was size 3. We're doing 3 boards at once here, and the computer is complaining that the loss function outputted a vector of size 3. If I wanted to be extra sure, I could print out the loss and make sure that is confirming what I have here. So I could do the loss of params, boards, and then my returns, I guess, was the thing that I called the returns. And if I run that, you'll see indeed it is 3 different numbers. Right now, the computer doesn't like it when you do things out of order. So I ran this to get the loss, and then I ran this above it. So it's saying, hey, I don't know what that is. If you switch the order, it'd be fine. But if you run them, then it's okay as well. And so indeed, this is a vector of size 3, and you cannot do the gradient of a vector of size 3. You would get like 3 different gradient vectors. And JAX.grad cannot do that. So that is the bug. If you selected that, you got the right answer. So very nice. You can't do the gradient of a vector. If you do the gradient of a vector, that's some other thing. The gradient is, that would be like the derivative matrix or something. For a scalar value, that's what we do the gradient of. And that is what JAX expects. So how would I fix it? Well, let's go over here. How would I fix it? Anyone have any ideas of how to fix it? Yeah.
Vectorize the gradient.
Vectorize the gradient. So yeah, you want to get like the different entries. So get the 0th entry, get the 1st entry, get the 2nd entry. So that's one way to do it. You could do some kind of like for loop. Again, once you do the for loop version, then you can speed it up by vectorization. But the for loop version would look something like this. For B in boards, get the board, and then do the grad of boards of, okay, let's do let's do it like this. Let's call this index, and my returns of index, and we'll make the index go in the range of the number of boards, which I guess is n batch. We know what that is, so let's call that n batch. N batch. So that would be one solution over here. Okay, so these two go above. This one goes below. And there we go. So let's see if this would work. So one at a time, does this work? And it does. Okay, this works perfectly fine. And so now we have fixed it. We have run them individually on each board individually. And now it is an actual scalar. And it's totally fine. So yay, we did it. That's the for loop version. Now we want to vectorize it. And to vectorize it, you have to think, once we have the grad, I guess now we have the grad for the index. What are we doing with the gradient? Well, we're using the gradient to update the parameters. So we would update the parameters when index equals 0. We would update the parameters when index equals 1. Then we would update the parameters when index equals 2. And so if you had a thing over here, you would be sort of adding them on, then adding them on again, then adding them on a third time. Instead of sort of keeping track of them individually and adding them on every time, how could we speed it up and just add them on all at once? I guess this is another way of saying how do we vectorize this for loop away? Yeah. Yeah, you could do VMAP. Okay, so you could VMAP it, and then that would get rid of this for loop, and you would still have all the individual gradients, and then you would apply them one at a time. But I want to think of a way, instead of applying them all one at a time, is there a way I can apply them all at once? So that's the right kind of idea. Yeah, in the back.
Where do you stick with the mean?
Yes, the mean. Where do you want to put the mean? In the loss. Yeah, so this is a nice observation. We don't actually need the gradients individually. I don't need the gradient of number 0, the gradient of number 1, and the gradient of number 2. What am I going to do? I'm going to take all three of them and add them to the same thing. So I actually only need the sum of the gradients. So why don't, instead of doing the gradient of each one individually and then adding them up, why don't I add up in the loss function and then do the gradient just one time? So we know from calculus class that sums play nice with gradients. So here is a very simple solution. You could do the sum out here, JNP dot sum, and then you could just add this up. And what that will do is I'll convert the vector of size 3, the values, it'll add them all together and tell us the total of all that. And then when I do the gradient, it'll automatically have the total from 0, 1, and 2 all together. So let's do this. So this was the old way. Let's put this back. And actually, why don't I do a little check here before I run it? Okay. I have forgotten a bracket somewhere. Okay.
It's around the very end.
Very good. Okay.
Oh, does that matter? You need to.
Yes, normally they're color coded. So this blue one is on the outside. This green one goes with that green one, and this brown one goes with that brown. Okay, very good. So now the loss function is returning one single number. So I can check over here. It's not 3 numbers anymore. It's just adding them all together. And then, if it's adding them all together, then I can do the gradient just once, and no one will complain. So the gradient, it can be the loss. And now everything's fine, and it's automatically doing the sum. So instead of doing it in a for loop and adding them up, I can sort of give up on knowing what each of them is individually, and I can just put it in the sum, and now it'll be nice and fast, super vectorized, and super speedy. Yeah?
So the loss does require that square?
If you want to do the loss that we were doing, yes.
I was like using it, and I was told otherwise to not.
Well, okay, so if you want to write down the loss, you have to write it down with a square. Another option is you could do something like this. You could do JAX.grad of just the value function, and then you could put in the params and the board, and then you could manually put in the difference. So you could do value of params board minus return. Okay, so something like this. So you can sort of, if you do the derivative of the square function, because you took calculus class, you know that the 2 is going to come down, and then you're going to end up with just the gradient of the inside, and the gradient of the inside is the gradient of the value function. So you can sort of write it out manually, or you can write it out like this as a loss, and then do it this way. Once you start getting more and more complicated, it is a little bit easier to write it out as a loss. So for example, if I'm writing this one out, where do I put the sum? It's possible to go wrong. It's not too hard to work out, but you could make a mistake if you write it out this way, as I have here, the loss. Very crystal clear. You can also print the loss over time and make sure it's going down. So it's a little bit more straightforward to do it this way than this way.
Okay.
Yes, great question.
Yeah, I was getting that mixed up on my own time. So.
Okay. Okay. So there you go. Okay. So there we go. That was the solution to the mathematize at the beginning of class. If you do this, you'll get a vector. You need to collapse the vector down to one single number. And if you have multiple things you're doing in parallel, very often you just need to know the sum of all of them. There is one small improvement I would suggest, which I think was actually suggested to me. Don't do the sum. Actually, let's do the mean. Let's do the mean. And of course, everything still works. Everything is exactly the same, except now it's dividing by 3 throughout. Does anyone know why it's slightly better to do the mean than the sum?
Supposedly the gradient doesn't blow up.
Yeah, so the thing that's going to happen is right now, I have 3 boards, and maybe I'm trying to get my program working, and I'm doing 3 boards at a time, and I get everything working. And then I'm like, yay, now let's do some serious training. And I blow it up to 3,000 boards, and I'm like, we're going to learn 3,000 games at once. If I had done sum, then all of a sudden, the loss is 1,000 times larger than it was before. So because it's adding up 3,000 things instead of 3 things. So by doing the mean, I can sort of get parity between the situation with 3 boards and 3,000 boards. And the 3,000 boards should just run better, and everything should work fine. If you do sum, you have potential bugs when you start to change the end batch. So by doing mean, it's kind of like more invariant under the size of the batch, and you hope that that makes things easier. So that is better for your life. You should do that. Question over here, yeah.
Does averaging out or summing in the value function lose some information that we need by just training on the individual games?
Yeah, that's a great question. In the way we've been thinking about them, like you have a large number of samples and you're treating all the samples as like all equally good, then you don't lose anything out. Like we were going to add them together anyway. When we did the gradient descent step, we were going to add them all. It's true, you could maybe do something smarter. Like you'd say like, oh, the ones where the gradient is super big, like do something special. So there's like fancy things. There's something called proximal policy optimization, where what you do is you make sure the neural network is not changing too much. So you're like, I know it's pretty good now. Don't make any like sudden movements, okay, man? Like just like small movements only. And then you could do something like, before you take the mean, you could like, if they're too big, shrink them down. So give them like a cap to make sure you're not taking any one game that's like super weird, that's like really out there. Don't be overly influenced by that. And this kind of thing is really common in a lot of situations because otherwise your model will just like, it'll find like weird ways to like solve the problem and not do what you want. A good example is for a long time people trained on these Atari games and they had like, here's the picture of what is on the game console and try to make the score as high as possible. But then the reinforcement learning algorithm would find bugs. Like it would be like, oh, if I go like back and forth like this, then like I gain 1 point every time I do it, and it wouldn't like play the game. So if you let it do like crazy things, it can do crazy things. So sometimes people do that. But for what we're doing, should be fine to just take the mean. Great question. Okay, anyone else? Okay, well, 4 other people were worried about the tuples, which is what we left off with last time. So you'll notice that the gradient is a tuple. Let's see if my parameters are working today. And indeed they are. So the parameters, it is a tuple of 6 objects. Why is it 6 objects? Because if you recall in my the way I was using them, I was saying W1, B1, W2, B2, W3, B3 are the parameters, and then I was using them. And then when I made the parameters, I was also making them like this. So I was returning W1, B1, W2, B2, W3, B3. So their parameters, it's no longer just one big vector like you guys did on your tic-tac-toe project. It is now 6 vectors of varying sizes. So I could ask it to please print out the sizes, which I did over here. So if you do this, you'll see we got 6 things over here. Oh boy. Okay, yeah. So here are the 6 things, 48 by 64, 64, 60 by 64, and so on. 48 by 64, is that 4? Oh, 16 times 3. Okay, yeah, great. Okay, 16 times 3 is 48. Okay. So these are the different shapes. 48 is the input, then we do a bunch of stuff. We get to a 64, and then we're finally down to a 1. So it's not just one vector anymore. And this is quite annoying because if you try to do stuff, this is what we left off with last class. If you do params minus equal alpha times the gradient,
and you make alpha some number, alpha equals 0.01, and you do this, or even if you try to do it fancy, say like params equals params minus, then it will yell at you and it'll say, you can't do that. You cannot do the difference of two tuples. So tuples, unlike vectors or arrays, they do not have an operation minus. They do not have an operation of alpha times, like a scalar multiplication. So instead what you got to do is you got to do some sneaky stuff. Here is one way to do it in Python, which is I call this the tuple minus function. And what it does is it does the function x minus y, and it applies that to all the things from tuple A and all the things in tuple B as pairs, and then it does a map. So the map says do it to all of them, and then turn it back into a tuple. So this will work. This was suggested to me by ChatGPT, but it's a pretty common thing. And now the parameters get updated. So the parameters just subtracted tuple B. I guess you might also want to include the alpha value, right? Alpha or something. And then you do x minus alpha times y, whatever you want, to subtract the other one in a different way. So that's one possible solution, is to write some function like this, or some loop that kind of changes all of the entries of the tuple in one way. This one is quite slow because map will return a list, and then you'll do a bunch of list operations and then convert it back to a tuple. So this is like actually a huge mess. Fortunately for us, JAX has this built in. So there's a function called tree map, which will take everything in a tuple and apply whatever you want to both tuples. And in this case, I'm just doing the difference, a minus b. That will work perfectly well. One adorable thing about JAX is this tree map function also works for other things like dictionaries. So you could do something, you can do something silly. Like you can do, I have a dictionary where the weight is 1 and the bias is 7, and I can subtract, the weight is 3. I guess let me subtract 0.2. I'll subtract things to keep them positive. And 3, and then I can do like new dict. And this one you really know you're going crazy because you're like, I'm going to subtract these two dictionaries. What does that even mean? But JAX knows what you mean. So if you type in the new dictionary, it will be sort of the difference of the old dictionaries. So it took 1 minus 0.2 to get 0.8, and it took 7 minus 3 to get 4. And so sometimes people keep track of their weights and biases in dictionaries rather than in tuples. That's another common thing. And then they have sort of names, which is cute. So some people like that. So that's what this JAX.treeMap does. It's sort of typical in JAX to keep track of not just one vector at a time, but arrays of vectors stored in tuples or dictionaries or other weird containers. Okay, so there you go. That's how you subtract your tuples. Questions or comments about that? So one other trick, and I think I promised last class, you'll never have to do this because you can just use the trick. And the trick is using an optimizer. So there's a package called optax. Okay, we're going to use these boards in a minute. I'm going to train it to do some boards. But there's this package called optax. So everything in the JAX ecosystem ends with ax. So optax stands for optimizer JAX. So that is the package for optimizing. And you can make something called an optimizer by doing optax.atom. I think you can also do optax. If I do optax.gd, let's see if that's a thing. Oh, nope. What about sgd? Sgd? Yeah, okay, it works. So if you do .sgd, it will literally do exactly what we've been doing. It will just always be subtracting the gradient. That is called stochastic gradient descent, or SGD. If you do atom, I think this one was introduced right at the end of last class in PyTorch. Atom is a different optimizer that changes the learning rate based on what it's seen, and it's quite a bit better than SGD for things. So because it's no extra work, you might as well use atom. And this is how you would initialize things. So the parameters are initialized. The optimizer, you have to feed in the parameters. So you do optimizer.init of the parameters, and the optimizer state keeps track of what is going on with that optimizer. And then you would learn things like a loop like this. So here is the kind of way you would update the parameters. You get some gradient, and then you feed the gradient into optimizer.update. So you do optimizer.update the gradient values you saw and the optimizer state. And the optimizer state will keep track of making the step sizes bigger or smaller depending on what's going on to try to improve things. And then to actually get the
new parameters, you do what's in line 4. You do apply updates of the parameters. So by doing apply updates, that is like doing the adding of all the tuples for you. So that's a very nice way to do it. And here is a little example that I wrote. Let's see if it'll work. So I have a batch size of 1,000, and I'm doing 1,000 iterations. So I'm doing 1,000 boards at once. And what am I doing? I am making some random boards. So random boards, 4x4, filled with 1s and 2s. And I am figuring out who won the game. So the return is who won the game. And then I am trying to train the network so that the parameters, so the value function matches this. And I have it printing out the RMSE. So let's take a look at this. How long will this take? We're going to find out. OK, like 30 seconds. OK, fantastic. So it started out with an RMSE of 0.87. So the correct answer is between -1 and 1. So if you're off by 0.9, you're pretty far off. But then over time, it's getting better and better. So here, the RMSE has gone down to 0.24. It's off by like 0.24. And so here it has learned 0.2. Let's see how low can we get. 0.15. And finally, 0.1 something. And here's a nice little plot. So it's learning over time. It's getting better and better at learning for a filled-in board who won the game. So this neural network has now been trained. It's quite accurate. If you give it a board that is filled with 1s and 0s, it will figure out who won. Let's do a little example. I'm very actually curious how good it is. So, oh yeah, okay. Okay, this has 1s and 0s. So give me some 1s and 2s. 1s and 2s. Let's put in some 2s here. 2, 2, 2. I guess I got more 2s than 1s. Let me add in some more 1s. 1, 1. And okay, so that's the board. Why is it okay? I guess I want. Let's just ask for the value function. Value of params board. Params board. So the neural network thinks that player 2 won. So it thinks for this board, player 2 has more 3s and rows than player 1. I guess to check it, we have to print the board and count. Print board. Who won this game of tic-tac-toe? So player 1 has 1, 2, 3. Does player 2 have more than 3 in a rows? 1, 2, 3, 4. So player 2 did indeed win. And our neural network knows that it won. So there you go. Our neural network learned something useful. This kind of thing might be useful for your game. Of course, the real trick is learning which moves are good or bad when there's empty squares on the board as well. So it's kind of easy to tell when the game is over who won. Not a big trick. Your job is to do it for empty games as well. Okay, I think that's all I wanted to show you for these JAX neural networks. We're going to start something completely different. This is a great time to stop for questions. So once again, your assignment 5 is now posted on the auto grader as well, so you can post it. You can post and see how you're doing. There's 2 versions. There's a version that runs 1 game at a time, and there's a version that runs 10,000 games at a time. Ideally, you'd get the 10,000 game at a time one working. If you do certain things, weird things in your function, the VMAP won't work, but definitely try it out. And yeah, so for assignment 5, you only have to play against the random AI, and you only ever have to know which move to play. You never need to know roll again or not, because you're going to always choose to not roll again. And then for the final project, it'll be the same thing but bigger, and you can choose whether or not to roll again. And there will be some mystery AI that you will compete against, who's generally good at tic-tac-toe, that you have to see how well you can do against them without specifically training against them. All right. Questions? Comments?
Why do one-shot encoding instead of 3 values?
That's a great question. So the reason it's better to do one-hot encoding instead of 3 values is because we are doing all these linear operations. So for example, I take x times w1. The way I did it, x is 1-hot, which means if there's a 1 in there, then I use a certain parameter. If there's a 2 in there, I use a completely different other parameter. And this lets the neural network know, oh, if there's an x there, I'll do one thing. If there's an o there, I'll do another thing. If I wasn't doing one-hot encoding, and I just fed in the board, then the neural network would have to do twice as much stuff for a 2 rather than a 1. So it'd have to say every time there's an O, that's double the amount of parameter as a 1, which doesn't make sense in real life. So the one-hot encoding is good if you want to give the neural network the flexibility to do sort of a completely different thing for 0s and 1s. And not one-hot encoding is if you want to have like a sliding scale. So like, maybe there's a neural network that's like, how long is this fish? Then I wouldn't one-hot encode it. Yeah. Question in the back.
I suppose given that it's how would I use more modern coding to check for, like for example, if they're in a line or both if they're in lines?
Oh, yeah, this is a great point. So I just fed in the raw states of the board, but you can feed in whatever you want. So if you want to feed in where the 3 lines are, that's a great start. So like your job is to make the whole neural network. And you know, this kind of stuff is pretty standard. Like neural networks, these fully connected ones have some number of layers and some widths. So there's only so much you can do. But you can absolutely play with any kinds of inputs you think are helpful to the neural network. And actually, you'll notice I left one thing out. This neural network inputs 0s, 1s, and 2s. Are those the only things that can happen in pig-tac-toe? No, people are shaking their head. There's also a negative one, which is the potential pieces. So the neural network should also input the negative ones. Of course, you could input them just in like, you have a 1 hot for the negative ones. But of course, the negative ones have something to do with the ones, right? Like they're kind of related, because if you choose to stay, then the negative ones become ones. So it's your choice how you're going to feed that in. You're going to play with it, see what works, what doesn't work. Okay. Yeah?
Just for like a sense, like how many times would we need to run it to learn the parameters?
Yes, this is an absolutely $1 million question. So the thing is, it depends on a lot of things. So one is how many parameters you have. You'll notice here I already have way more parameters than there are like states, right? Because just the first layer on its own has 48 times 64. The second layer has 64. The third layer has 64 times 64. And then 64 and then 64. So there's like some thousands, like 64 squared is a big number. There's some thousands of parameters already. So you should expect at least to run like that many games, which is it's very good that I can run like 100,000 games at once. Otherwise, we'd be here all day. And so the bigger you make your network, the more parameters you have, the more like flexible it is. It can learn all sorts of weird patterns, but the more it's going to take to run. So I think one way to do it, and this is what is done in real life, is you start small and you like build up. So try a small network first, get it working. A small network should still be able to learn, but will have some sort of like ceiling of like how good it can get, because it just like can't possibly learn certain patterns. It's like out of memory for its parameters, and then scale it up from there. It also will depend on the learning rate. So if you make the learning rate too big or too small, then things will go bad. Here I made it 0.01 to 0.001 is a good range. If you make it too big or too small, weird things can happen. If you make it too small, then it will learn very slowly. So let's see what that looks like here. Let's plot out the first 100 of this. You'll see that it should sort of not be going down very much. So you see it's kind of like barely going down here. Where so I make it too big, then things can go wrong the other way. Things can start to explode. But actually, probably this will be okay. So by looking at these plots of error versus time, how is the error going, you can get things better. Okay, look. Here, something went totally wrong. My root mean squared error went all the way up to 18. I was trying to estimate a number between -1 and 1, and I'm off by 18. That's real bad. So I made the sort of step size too big, and now it totally exploded. So probably I'll go back down to maybe -3, and hopefully it'll work better. Okay. There we go. See, that's much better. Much more reasonable. So by doing these kind of plots, it can help you diagnose these various issues. And yeah, nobody knows the answer to how long it will take to learn. Yeah.
Related to this, what the good alpha would be, I considered in my assignment before having a changing alpha. So if we were to
Yes.
do that, would we consider like the average or maybe like?
Yeah, this is a good idea. So alpha is sort of like how much you are changing what you had before to what you had now. So if you're pretty sure what you had before was already pretty good, then you want a smaller alpha, which is like don't update too much. So a good idea is to make alpha start sort of relatively high, and then over time make alpha smaller. So if you have a really good neural network and you're just like tuning it just a tiny bit, then maybe a really small alpha will help you. Some of this will be done automatically in this atom thing. So if you consistently get a bunch of gradients that are kind of small, then the atom will change the size and so on. But it's a good idea if you want. You can, maybe you change something. You like, I was learning this way, now I'm introducing this new thing to reduce the alpha value. Yeah, and again, I can't tell you the answer to what's a good way to schedule it. You have to sort of guess and check. You can try to look up some theories online. Yeah. Okay. Other questions or comments about your assignment 5? Okay. So we're going to start something new which is related to something we've been doing a lot. And so far, we've been doing the kind of easiest possible thing, which is this epsilon greedy. So remember, the reason we have to use epsilon greedy is because otherwise we get stuck sort of in a corner of just trying the same thing over and over again. And when you try the same thing over and over again, obviously you have no potential to learn. You have never seen anything other than the situation you're currently in. So instead of doing epsilon greedy, we want to try to think of a smarter way to do some exploration. And so I will let you guys think for a minute to come up with some ideas. And then I'm going to show you one in particular that is quite cool. Okay, while people are finishing this up, I'm going to hand these out. You should try to get one of each color. So there's 4 colors. You need one of each color. Okay. Need one more. You have it. Okay. Did you go on? Okay. Or this might be my set. I'll take it. Yeah.
We only need one each.
We only need one each. Okay. Okay, we have 15 answers, so we're going to talk about epsilon greedy and improving epsilon greedy. And epsilon greedy, as you might have, if you've thought about it, you'll realize it's silly in a number of ways. Let's see what people thought. So how could you improve it? Ooh, okay. Amazing. Lots of words here. Okay. So one thing we've talked about is changing the epsilon rate, right? So at the beginning, epsilon should be high. You should explore a lot. And then as you're more and more certain, you can decrease that epsilon. Eventually, you can decrease it down to 0. So like if your AI is pretty good and it's not getting like stuck in the corner, then you can decrease the exploration down to 0. So very nice. Another way you can sort of replace this epsilon greedy is by starting from random states. So if you know the rules of the game, you can say start playing the game from this board and try to improve that way. And that can replace out the epsilon greedy, which can also be quite a good thing. Okay. So the epsilon greedy chooses moves that are not recommended by the policy, right? It doesn't choose the best possible move, but it chooses purely at random. So like the policy says, this move is the best, these other moves all suck. And the epsilon greedy says we're going to choose one of them purely at random. And that is one possible spot that you can improve it, is where the epsilon greedy does choose something not recommended by the policy, but maybe we can do that in a smarter way. Okay. Yes, okay. So depending on which ones you visited or not visited, maybe we can make some smarter choices. So all of these things are all right. Non-constant epsilon is something we've talked about. Okay. So these are the right kinds of ideas. And so we're going to start with a very simple, instead of taking some complicated thing and putting it into our algorithms, we're going to start with something extremely simple, which I call fishing at the lake. So here is my little animated thing. And so imagine you're a fisherman and your reinforcement learning task, there's no turns or anything. You're going to do one thing. The only thing you get to do is decide which of these lakes, lake A, B, C, or D, you go to. That's the only thing you get to decide. So it's like a reinforcement learning task with one state, which is you're at the lake, what are you going to choose? And when we learn the answer to this, we're going to then be able to scale it up to our other problems. So here's the specific setup. So we're going to go on a fishing trip. The trip is going to be T days long, and we know T in advance. I think when we do it, it's going to be 40 days. So a nice long fishing trip. T is a big number, and we have L different lakes to choose from. So L stands for lakes. We're going to have 4 lakes, which is why you have 4 pieces of paper. You're going to vote for which of your favorite lakes you want to go to. Actually, maybe this is a good chance you guys can label your lakes now. The lakes will be labeled A, B, C, D. What? So we're going to add a quick vote. So here's A, B, C, D, green, red, blue, and yellow. You make sure you do it like that. Otherwise, I won't know what you're doing when you hold it up. But you're going to have A, B, C, D, and you're going to tell me what lake you want to go to, and then we'll go to the lakes and see how the strategy unfolds. So let me also, on my set, write them down so that I know what you guys are voting for when you hold them up. So A is green, B is red, C is blue, and D is yellow. A, B, C, D. So those are the 4 lakes. And so every morning you wake up, you get to decide which lake you want to go to, and we go to that lake. Because there's a group of us, we're going to vote, but that is the game. Should I write these on the board or something? No, I guess you guys will figure it out. Okay, let's go back to... Okay, so L lakes, for us, L is going to be 4. Okay, so you get to go to one lake, and you spend all day at that lake. You can't switch like lakes halfway through the day. So you spend a whole day at that lake, you catch fish. And here's the thing. Some of the lakes are actually better than the other lakes. So not all the lakes have the same distribution of fish. Some lakes you'll catch more fish at, some lakes you will catch less fish at. But of course, on any individual day, you don't get to know what would happen to you at that lake. On average, you get a random sample. Every lake has a different probability distribution, and when you go fishing at that lake, you get an independent sample from that lake. And this is an important assumption. Days of fishing are independent. The number of fish you caught on Monday does not affect the number you will catch on Tuesday. So if you go fishing 2 days in a row at the same lake, you just get 2 independent draws of the lake distribution. Okay. And you want to maximize the total number of fish you catch on your long fishing trip. So this is like some kind of abstraction of doing your reinforcement learning problem where you're at a board and you have T samples. So for us, T is the number of days. For you, T will be the number of times you play through the board. And L is like the number of choices you have. It could be up as high as 9, but if some of the moves are illegal, it'll be lower, right? So it's kind of an abstraction of what we've been doing with the reinforcement learning, but just a nice simple, the same choice over and over again. Are there any questions or comments about the setup? Did everybody get the A, B, C, D? Okay. All right. So this thing is called a bandit algorithm. You'll see why it's called the bandit algorithm in a second. So this is the bandit setup. I'll tell you, a very funny name. I'll tell you why in a minute. But before I tell you why, let me show you some actual uses for this thing. So this exact problem is used at Netflix. And in fact, they have a very nice blog post where they describe this. So Netflix, when you log into Netflix, they choose to show you on your screen, when they have a new show, they can show you one of many different possible thumbnails. And they have made, for each of their shows, they make lots of thumbnails. And then they decide, this user likes this type of thumbnail, this user likes that type of thumbnail. But how do they know which thumbnails are better and which ones are worse, right? So when they're first starting out, new season of Stranger Things comes out, they're like, we're gonna make all these thumbnails. How do we know which one's better? Well, for them,
instead of T days, they have T customers. And for every single customer, they have to show them one of the thumbnails. And that's just like us. For every single day, we have to pick a link. So T customers coming to see Netflix, we can choose one of the L possible thumbnails to show them. That's just like the links. And the fish is what we had for the links. And here we have clicks. So you might imagine some of these thumbnails are way better than the others. And we want to visit the thumbnails that are very good and not visit the thumbnails that are bad. Figure out which links are bad and don't go to those ones. So that's the analogy. And maybe I'll talk about this later, but Netflix also has some smart ways to incorporate neural networks in that. So not everybody sees the same thumbnail, but still knowing which thumbnails are good or bad can help them. So that's the analogy, lakes or Netflix. Here's another analogy that might be closer to your heart. What about for games? Which moves to analyze? So here is a game of chess. On the opening of chess, apparently there are, 18 possible moves you can make. Which move should you make? And more importantly, if you're an AI and you're spending computational resources thinking about them, which moves should you consider a lot? So should we spend a lot of computational time thinking about this move where we move our pawn up 2 in the corner? Or should we spend more of our computation time thinking about this move where we move our king pawn up 2? Which one is a better use of our computing resources, right? And one thing you could do is the sort of like everybody equally likely, spend 100 cycles thinking about this move, and 100 cycles thinking about this move, treat them all equally. But then you might spend a lot of time thinking about moves that aren't very good, and that's kind of a waste of time, right? And so, again, this is an analogy of our situation. Instead of T days, we have like T simulations worth of computing. We have L possible moves, and we want to spend our time thinking about the better moves and not thinking about the worst moves. So just like we want to go to the good lakes and not the bad lakes, we want to prioritize which ones are better and worth it before we make our move. So that's the analogy over there as well. And there's an algorithm built on top of this called AlphaGo 0 that I'll explain after we go through these things how it works. Okay, so that's AI for games. So this thing is called a multi-armed bandit problem, which is why in the literature people call these bandits. You could say I did my PhD in bandits, which is like a thing, which sounds very funny. Why is it called bandits? Well, a one-armed bandit is a slot machine. You pull the arm and it takes your money. So it's a one-armed bandit. Okay. What is a multi-armed bandit? Here it is. It's like a bunch of slot machines. So you have many, many slot machines. That's a multi-armed bandit. And just like the lakes, you can think of each arm as a different choice. So we have L arms, and every day you have to pick one, or every play you have to pick one. Maybe some of the slot machines only take a little bit of your money, and some of them take a lot of your money. Can you figure out which ones are good or bad? Okay, that's the analogy in the question. We're about to try it out. So I have a little bit of a little simulator here, and you guys are going to tell me which one to do. And then we're going to see there's an AI that's also going to play it, and the AI is going to see, we're going to see if we can beat the AI. So this one, the AI scored 359 fish, and the humans scored 357 fish. Sorry, humans. Better luck next time. Okay. And in this particular situation, arm C was the best, but it's random every time. So here is what it looks like. This is the little simulator. Bandits.html. Let me see if I can get the zoom just right. There we go. So our fishing trip is 40 days long, and every day you can visit lake A, B, C, or D. These N values tell us the number of times we've been to that lake already. Today is our first day of fishing, so we've been to none of the lakes. And the average will tell you the running average as we go. There's also, as we go, the number of fish we caught will pop up down here. I'll show you that as well. But to start with, this is the fun part of the fishing trip. Which lake should we visit first? So you can hold up your letters and tell me what you want to do first. Okay. What's the order of what?
Is it green, red?
Ah, yes. Okay, this is important. Let me write it down. A is green. A is green. B is red. C is blue. And D is yellow. Okay. So I'm seeing a lot of A's. Maybe about half the people are A's and everybody else is split. So we're going to go to Lake A. We went to Lake A one time. Our average so far at Lake A is 9. That's because we caught 9 fish on our first day at Lake A. Now it is day 2. There are 39 days remaining. Where would you like to go fishing? All right, I'm seeing a fair bit of B's. Pretty big majority on B. At Lake B, we caught 8 fish. We've been to Lake B one time. We've caught 8 fish. Where should we go on day 3? All right, C, very popular. You guys are very alphabetical.
And day 4, where should we go? Okay, D. Okay, ooh, only 4 fish at Lake D. Where should we go next? Okay, I'm seeing about half the people in A and other people are supposed. We're going to go A. All right, so A, day 2, we caught 7 fish. Our average so far is 9 plus 7 divided by 2. 8 fish on average from Lake A of our 2 visits there. Where should we go next? Okay, this time I'm seeing lots of C's. Let's go to Lake C. Lake C, 8.5 fish on average. Where should we go next? Okay, this one's interesting. I'm seeing actually quite a few people on B. So 1, 2, 3, 4, 5, 6, 7, 8 people on B. That's the majority. We're going to Lake B. We caught 7 fish at Lake B. Okay, this is very close. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. It's a 7-7 split between D and C. You have to, you're the tiebreaker. Okay, you want C or D?
D.
D, okay. Oh, caught 8 fish on Lake D. Where should we go next? Okay. C, very popular. Let's go C. Okay. Only 5 fish that day. Where should we next? All right. Looks like B is winning by a little bit. B. People are still on B. Oh, some people are on A. 1, 2, 3. Oh man, 6. Very split vote here. Okay, I think it's 6 in A, 4 in B. Okay, so 6 in A I think is winning it. All right. Okay, now we got B's and D's. 4, 5. Oh yeah, okay, we got B. B. People like B. Okay. Lake B. Where to next? B. B again. Ooh, okay. Where to next? Okay, now it's all over the place. Nobody knows what they're doing anymore. Okay. 1, 2, 3, 3, 4. Oh, B. Okay, C. C is popular. Okay. All right. Where now? C. People are liking C. Okay, C. Oh, we only caught 5 fish that day. All right. Now everyone wants A. A is the one. Okay. Now everyone's in D. Oh, Lake D. Letting us down. Okay, I'm seeing B's. Lots of B's. People like B. Okay, B. 6 times a B. Okay. Now C. Now everyone likes C. Okay. All right. Where now? Okay, still C, I think. Okay, let's take a little stock here. We've done half our fishing trip. So we started with 40 days left. There's 20 days left. If we start doing the same thing over and over again, we can start using these ×5 buttons where we go to the same lake 5 days in a row just to speed things up a bit. But where do you guys want to go now? I'm seeing lots of C's. People like C. Okay, C. Ooh, okay. Still C. Oh, it went down to 7. We only caught 5 fish that day. All right. C. C again. Okay. C again. C again. Anyone changing out of C? No? Okay, we got a couple people in D, but not enough. Okay.
Come on, guys.
Okay. Do we want to change now?
D. Screw it.
So we got only 1 fish in Lake C that day. Our average is down to 6.38. You guys want to do C again, or do we want to do a different one? Okay, people are switching to B.
We moved data
In B.
in D.
Okay, 10 plays left. What else we got? Okay, I think people are liking B.
You know what?
Anyone changing? People are changing to A. Okay, very interesting. I think B is still winning here. B. Okay. Do you guys still want B? We got 2 fish that day. The average down to only 6 fish per day in Lake B. Okay, now you guys are really all. This is the problem with democracy here. Everyone is split. I think A is winning, surprisingly. Okay, A. A. Okay.
D. Let's do it.
I'm seeing. Okay, 1, 2. Okay, I'm seeing C's. Let's do some C's. All right, and now okay, still C. I think. Anyone changing? C. C. Oh. D. This is how they do it at Netflix too. D. I'm seeing some D's. Okay, right now D is winning. There's 3 D's, which is winning the group. 1, 2, 3. 1. Okay, yeah, D. People like D. Okay, now people are getting out of D.
Wait.
All right, I'm seeing some A. 1, 2. I think A is winning. All right, we're out of time. We caught 233 fish. The AI caught 239 fish. It turns out the best lake, in real life you never get to know this on your fishing trip, but in this game we do get to know this. The best lake was Lake C. And Lake C has an average advantage of 1. So every time you go to Lake C, you catch 1 more fish on average than the other lakes. So C is a little bit better. You guys went to Lake C 20 times. Congratulations, it's very good. The AI only went to Lake C 17 times. But nevertheless, the AI caught more fish than you. So that was good for them. Let's see, what else did they do differently? So the AI did 6 times at Lake A, 12 times at Lake B, 17 times at Lake C, and 5 times at Lake D, just like you did, and it caught slightly more fish than you. So this is supposed to help us figure out what is the right way to think about this problem, what are the right strategies. I think you are starting to see some of them. There's 2 strategies that we've talked about so far in the course. So one of them would be the greedy strategy. So if I reset this, the greedy strategy would be something like pick whichever lake did the best. I guess in this situation, Lake A and Lake D both did the best. And let's do a tiebreaker over here. So Lake A is the best. The greedy strategy would say, let's just always go to Lake A. So there we go. Lake A, I went there every single time. I got 302 fish. The AI got 315 fish, and that's because Lake B was the best. So I spent all my time at Lake A, even though Lake B was the best. That's the greedy strategy. I think towards the end, some people were playing greedy and some people were not. So some people were voting for whichever had the highest average, which is the pure greedy strategy, and some people were not. So that is one possible strategy. So let's write down some strategies. Let me see if I can get a little board over here. Okay, so greedy. Always play the lake with the highest. Okay. And it turns out the greedy strategy is actually quite bad here. So this is the same idea of getting stuck. The greedy strategy can get stuck. What do I mean by get stuck? So it can get stuck. What does that mean? What? So this is actually the first part of this problem, is figuring out what do we mean by good or a bad solution. What does stuck even mean, right? So in our learning algorithms, we had this notion of you're playing through many, many states. And so stuck has a nice interpretation of you're seeing the same states over and over again, right? Your Roomba, instead of exploring the whole room and figuring out what to do, keeps going in this corner and it's just like not exploring. In this game, you're always, at the lakes, you always have a choice of lakes A, B, C, D. So you can't define stuck by not visiting states. We're always going to be in the same situation where we can choose the A, B, C, D. And nevertheless, you can kind of have the same kind of idea of, I was doing the greedy algorithm. I was just doing A over and over and over again. And that didn't work for me. Okay, well, I guess I looked only at the beginning and then I was greedy. So I was doing some kind of like greedy in the first 2 turns thing. But how would we define this idea of getting stuck, of like not doing the right thing? Is there a way you can kind of make this more precise, or like think about this? How would you define this? What are we even trying to do? What should we maximize? Does anyone have an idea of how they were thinking when they were voting? So I know some people were doing greedy, but maybe somebody who wasn't doing greedy would like to say how they were thinking about it and how they were distributing their votes to the non-best option. Yeah.
During the starting, I kind of voted for D like twice or thrice, just because I wanted to know if it's not the option, just eliminate it, so that we can focus on the other ones.
I see. Okay, so you were voting. So even though D wasn't the highest, you were voting for D.
Just in the first.
I see. Okay. So maybe the algorithm, instead of greedy, should be like first explore, then greedy. Okay. Right? And the idea is that if we first explore around a bit, then we can figure out which one is the best. And once we know which one's the best, Then we can be greedy, and the downside of the greedy, where you sort of pick the wrong one, that will be mitigated by this first exploring. Okay, so that's one possible choice. Was anyone thinking about it differently? Yeah.
I played randomly all the way.
You played random all the way, so you're like the traitor of the group. Actually, okay, so this is one thing. If you play random, you can be pretty sure what you will get. Like, we can analyze this exactly and see what it is. A pure random. So what are the pros and the cons of the pure random? Well, you're not going to spend more time at the best lake, but at the very least, you're going to spend a quarter of the time at the best lake, right? So in some situations, like if you want to make sure you don't miss out on the best lake, pure random can be a good strategy. So this thing, it's why is it bad? Bad only spends 25% of time at best lake. But the good of this strategy is spends at least 25% of time at best lake. So this is actually a really nice way to contrast this with the greedy algorithm. The greedy algorithm has some chance of picking the best lake, but it also has some chance of spending very little time at the best lake, right? And the pure random algorithm is like the total opposite. It's definitely going to spend 25% of time at the best lake, but it's only going to spend 25% of time at the best lake. So can we find some other algorithm that will raise our chances of spending a lot of time at the best lake and minimize our chances of getting stuck into this trap of spending too much time at a suboptimal lake and not cashing in? Okay, so these are some different algorithms. First explorer, then greedy. Was anybody thinking about it other than these ones? Yeah.
You make a different choice than last time if the average decreases.
Okay, so if the average, so you're looking at how the average is changing over time. So if the average decreases, so look at how average moves around.
I am cheating by sort of assuming the distribution is sort of normal though.
It's not normal.
Okay.
Yes. Okay, the distribution of each lake is not normal, but the thing that we will use, not this class, but next class, when we start to analyze it, even though the distribution of each lake is not normal, by the central limit theorem, the distribution of the averages will be normal. And so that this will come up, and this will tell us, how the things are moving around. So I guess if the average goes down, what do you want to do? Stop visiting that lake, or
Choose to explore.
explore more? Okay, so explore based on how much the average moves. Okay. Any other thoughts? Yeah.
Sort of like a confidence, like you want to maximize the confidence.
Okay, so confidence. Do you want to say what you mean by confidence?
Maybe like a standard deviation or something.
I see. Okay, so I'm gonna add this word interval. So a confidence interval is instead of just looking at the mean, we can try to build a confidence interval. And so if we look at our lake over here, these averages are the averages of the actual fish we saw. So the averages of lists of numbers. So it's a very well-defined thing. One of the things you learned in stats class is that averages, these are called point estimates, sometimes hide important information. And one of the things they hide is how much uncertainty there is. So instead of looking at the average, maybe what we should be looking at is some kind of interval. So on this board here, I kind of maybe tricked you guys by just writing down the average, or maybe what I should have written down was something involving like two numbers, like how confident are we that the average is between something and something else? And this is exactly what's going on here. We've gone to Lake A 36 times. We've got the average of 7.56. We can be pretty damn sure that if we were going to keep going to Lake A, it's going to be between 7.4 and 7.6. Like it's going to be very close to this thing. We have a lot of trips to Lake A. We have a lot of information to base that on. Lake D, we've only visited 2 times and has an average of 7. So even though the average 7 is lower than the average 7.56, we have a lot less information about Lake D. You can imagine the confidence interval for Lake D is much, much wider. And therefore, maybe we should do some exploring on Lake D. So shrink that confidence interval down until, then we can compare like apples to apples. So this one right now is higher, but much more certain
and this one is lower, but we have big uncertainty, maybe we can record that with a confidence interval. That's a fantastic idea. So here's what I'll tell you is the plan for next class and possibly the class after that. We are going to analyze these different algorithms, and we're going to come up with a number that explains how good each of these are. And we're really going to actually do exactly what you guys said. So we're going to do these 4 algorithms, and we're going to, when we do the first explore, we're going to optimize this. We're going to find the optimal amount. So when we come up with our number, it'll let us analyze these things, finding the optimal amount, and also how do we use the confidence interval. And the thing we are going to do is something called regret. That is the measure we're going to use to measure these different algorithms. Let's see if I can find the slides again. So, so here are some assumptions, but the thing I want to talk about is the regret. So this is the definition of the quantity that measures how good or bad something is. And regret, like loss, the higher your regret, the higher your loss, the worse things are. And here is the idea. Whenever you play a suboptimal arm, at the end of the fishing trip, you regret it. So if you go back to our fishing trip, it turned out Lake B was the best. Every time I was going to Lake A, I was like leaving fish on the table. I regret going to Lake A so much. That is what regret means. Every time you go somewhere that's not the best, you experience regret. If you go to Lake B, you get 0 regret. This is like the best you can possibly do. Just like loss, the regret is always at least 0. You can't have negative regret. And how much do you regret it? We've defined it like this. It is a mu star minus a mu A. Mu star is the average of the best arm, and mu A is the arm that you played. So if you play an arm that is the best arm, then you get 0 regret. And if you play a different arm, then you get regret based on the mean. So importantly, it's not based on the outcomes. It's based on the mean. So here, in the first fishing trip, Lake A got me 11 fish, and Lake B only got me 8 fish. But actually, Lake B was the better choice because it has a higher mean. So even though this one, we got lucky with the dice roll, I regret not going to Lake B and having an even higher, chances for a higher dice there. So the regret is based on the mean, and we are going to try to minimize this total regret. So the total regret is expressed like this. It's the sum over all the times you chose. So the sum from lowercase t going from 1 to capital T of the regret you got in round T. So it's of the actions you actually chose. If you chose to play arm 1, arm 2, all the way up to arm capital T, then you experience regret mu star minus mu AT at time t, and you add that all up, that is your total regret. Of course, the total regret, even though these are means, so there's no randomness in these actual quantities, there is randomness somewhere, and the randomness is what arms you pick. And that's because what arms you pick can be influenced by the random outcomes. So the regret, even though it looks like it's not random, because the choices were random, they depended on the random things we saw, that is a random number. And so what we're actually going to do is the expected total regret. So we're going to take the average, and here's another way to write the expected total regret. Instead of adding it up from time 1 to time capital T, you can do the number of times you visited each arms times this delta thing, which is I call the gap. So delta A is mu star minus mu A is how much worse is that arm than the best possible arm. For the best possible arm, that's 0. For all the other arms, it's something positive, and n is the number of times you visited it. So what this is saying is, instead of adding up over time, you can add up over the arms, and how often did you visit each arm. And this is how we're going to analyze this thing. What we would like to do is find an algorithm that plays the best arm a lot and plays all the other arms very little. If we can do that, then we'll have low expected total regret. So that is how we're going to calculate things. And so next class, we're going to see an analysis of these various algorithms that you guys came up with. And in fact, this last one is a really famous one called the UCB algorithm. And that's where we're going to, that's like the ultimate. This one, in some sense, has the best possible regret. And we'll see that next class. Okay, we'll stop there and see you guys on Thursday. Like I said before, you have everything you need to start working on assignment 5. All of this stuff is sort of like extra. You can take it or leave it for your final project. So yeah, good luck.